This presentation is on the subject of black holes. Now, general relativity tells us that mass curves space-time. And if there is sufficient mass, then space-time is curved sufficiently that light cannot escape. Carl Schwarzschild showed that for a static spherical distribution of mass, lying entirely within a radius r, then an event horizon will form at r equals 2gm over c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. And this result applies at all matter densities as long as all the mass lies within the defined radius. So we can consider different density examples and conduct a thought experiment to see the relationship between different matter densities and the Schwarzschild radius. And in this thought experiment, we're going to assume that we have completely filled a distribution of mass of radius r. Then the density d is defined as the mass per unit volume. And the volume is 4/3 pi r cubed, because we're talking about a spherical region of radius r. And then we can take the point that if the surface of the star coincides, or the surface of the mass distribution coincides with the event horizon, then r equals 2gm over c squared. And if we eliminate m from these two equations, we get r squared equals 3c squared over 8 pi gd. And all of these are constants except for the density. So what that tells us is the lower the density, the larger the Schwarzschild radius. So we're going to look at an intermediate density case where we have a spherical region of space and we place a small particle of matter, just 1 gram every cubic meter. And from the formula, we find that if we make this distribution of matter large enough, an event horizon will form at around 400 billion kilometers. So this shows that it's a thought experiment, it's not a practical experiment, but it tests the laws of physics in the sense that we know that that formula applies, and such a distribution of matter would create an event horizon. And we can see that from outside of that distribution of matter, we would view it as a black hole because there's an event horizon there. But from within the event horizon, it seems like a fairly low density distribution of matter, and there's no physical reason for a singularity to form. And if you refer to Paul Dirac's book on general relativity, you'll find that there's no mathematical reason for a singularity to form at the center of the event horizon. So we're wrong to conclude that every event horizon must contain a space-time singularity at the center. I'm going to look next at the low density case, and looking at a spherical region with a density of around 0.724 hydrogen atoms per cubic meter. So less than 1 hydrogen atom per cubic meter. And you'll see later why I've chosen this particular value of density, because from the formula, it means that we would get an event horizon at 8.77 billion light years. And that 8.77 billion light years is a distance such that over a period of 13.8 billion years, it would take light 13.8 billion years to travel to our point of observation, starting from 8.77 billion light years. And that is simply because of the expansion of space over that period of time. And it would take around 28 billion galaxies at that time to achieve that density. So what this analysis shows is that the cosmic microwave background is consistent with the idea of there being a matter density at a time 13.8 billion years ago, which would lead to that event horizon. I should say that actually the 0.724 hydrogen atoms per cubic meter is the density that we would observe today, which is about a factor of 20 less dense than 13.8 billion years ago, again, due to the expansion of space. So now we'll look at the high density case. So we'll think about the highest possible matter density that we could achieve, and that corresponds to the density of a neutron. And if we then use our formula, we'll find that if you packed the whole spherical region closely with neutrons, and so that represents your density, an event horizon will form at around 10 kilometers and will contain a mass of around 3.4 solar masses. So this is what we would describe as a small black hole. And what this analysis is saying is that the smallest possible black hole is 3.4 solar masses, because it corresponds to the highest possible matter density. Now, previously it was thought that black holes only formed from collapsing stars, and that the collapsed star goes to a singularity. But there is no evidence of singularities, and in fact, a singularity is a place where the laws of physics break down, and it's something that we should avoid if at all possible. So it's not a conclusion that we would jump to lightly, and if we can find any explanation other than a singularity, we should seize on it. And there is no justification for concluding that matter can be crushed out of existence. It's not sufficient to suggest that the gravitational forces would possibly exceed the strong nuclear force, because the strong nuclear force is a binding force, and that doesn't mean that matter could be crushed out of existence. So there's no requirement from general relativity equations that there should be a singularity at the center of a black hole. Paul Dirac pointed this out. And the conclusion is that all black holes contain a neutron star of the corresponding mass. And this conclusion is supported by the observation that all black holes are greater than 3.4 solar masses, and all observed neutron stars are smaller than 3.4 solar masses. Now, most of the black holes in the galaxy form directly from dark matter, which is pairs of neutrons. Certainly, the supermassive black holes at the center of a galaxy could not have formed from a collapsing star. And after a galaxy formation event, a percentage of the mass, something like a thousandth of the total mass of the galaxy, falls into the center and forms a supermassive neutron star, which will be observed as a supermassive black hole. And we can get some ideas about the description of these black holes by looking at the analysis that we did earlier, where we said that at 3.4 solar masses, the radius of the star and the event horizon coincide at 10 kilometers. But when you increase the mass, you find that the event horizon moves out in proportion to the mass, whereas the radius moves out in proportion to the cube root of the mass. So for 3.4 million solar masses, the radius of the neutron star is 1,000 kilometers and the event horizon is at 10 million kilometers. For 13.4 billion solar masses, the radius of the star, the neutron star, is 10,000 kilometers. So something comparable with the volume of the Earth. And the event horizon is way out at 10 billion kilometers. So in these examples, of course, the mass is more closely concentrated towards the center and far away from the event horizon. Just a brief point on Hawking radiation. Hawking radiation has never been observed. It's based on the idea of quantum fluctuations in empty space. And in the space-time wave theory, which you can find elsewhere, the concept of quantum fluctuations in empty space is discarded. So the Hawking radiation cannot happen. Black holes do not radiate energy. And any object falling through the event horizon adds to the mass of the neutron star. And in this case, no information is lost. One final point, which gives further support to the idea that black holes contain a neutron star, and that is that after a neutron star merger, the combined neutron star may be rotating so fast that jets of radiation emerge at the axis of rotation. So you could imagine neutrons close to the axis of rotation separating into protons and electrons, and the protons rotating with the neutron star would create a magnetic field which ejects the electrons as a jet. And we observe the same jet phenomena in rotating black holes, leading to the conclusion that a rotating neutron star within the black hole is causing the jets. So this seems to contradict the idea of a black hole where nothing is allowed to escape, but it seems that the event horizon is open at the axis of rotation. That's what we could conclude from our observations. So, but we know that the Schwarzschild solution for a spherical closed event horizon only applies to a static distribution of mass. And if you're talking about rotating mass, then you require a much more complex calculation. And that requires further analysis, making use of the Einstein equations and computer modeling similar to that used on LIGO for black hole mergers. And that analysis would hopefully show how a rotating mass will form an event horizon, and if the conditions, the mass and the rate of rotation is sufficient, then the event horizon will be open at the axis of rotation. So that concludes the presentation on black holes. I think in summary, the presentation suggests that there is no singularity at the center of a black hole, and that all black holes are formed from actual matter, namely a neutron star, and the idea of Hawking radiation has to be abandoned.